Ladies and gentlemen, please give a big applause, a warm welcome to the Nobel Prize laureate in physics, Sir Geoffrey Hinton. He is just a hero of mine. Thank you very much. Thank you for your work. And of course, the show is doing, the interview is doing the Economist tech editor, Alok Jha. Thank you. The place is all yours.
Thank you very much. Welcome. I don't think I need to make much of an introduction, but I was thinking how to introduce Jeff. And you've already heard he's a Nobel Prize laureate, so what can you say more than that? Well, let me talk about the science. Well, I'm Alok Jha, the science editor at The Economist, and it's my pleasure to facilitate this conversation with Geoffrey. So Geoffrey is a British-Canadian computer scientist, cognitive psychologist, known for his work in artificial neural networks. And as you've heard, and as all the paraphernalia around this shows, he's also known as one of the godfathers of AI, which maybe you can talk to me about later. He's a professor emeritus at the University of Toronto, and for 10 years from 2013, he also worked for Google, which he left in 2023. Geoffrey, really nice to meet you. It's a real pleasure to have you here. I just want to start with a bit of a vision from you. So people here are talking about all the companies and the technologies that have come from various bits of AI. Is my microphone still working?
No.
Okay. It's back again. I'll shout if necessary. Anyway, they're all talking about the companies and the practical uses, but I'd like to start from you with some vision. So can you, in the most broad terms possible, tell me what the two or three most hopeful things you think AI will be doing in the next decade? What are the most exciting things for you? And in each case, would you mind just giving a sense of what you think will actually happen in those things, the concrete example?
OK, so there's nothing new in what I'm going to say. I think that AI will be amazing in healthcare. So in healthcare, I made a prediction in 2016 that in the next 5 years, AI would replace radiologists in interpreting medical scans.
How does that go? How's that going?
I was wrong. I got the timescale wrong. It's beginning to happen now. Right now, I think there's over 250 applications approved by the FDA for using AI for interpreting medical scans. It's used in major cancer clinics. I think it'll still be another 5 years before it's replaced radiologists, maybe even longer. The medical profession is quite conservative. But it will be able to get more information out of medical scans. So one case we know about is interpreting fundus images of the retina, where AI can see all sorts of things in those images that no ophthalmologist ever realized could be seen there.
And what about radiologists? What happens to them? Can they just treat more people, or do they disappear altogether?
So radiologists will still do many other things, like comfort people, plan what to do, although AI will, of course, be doing that as well. For quite a while, it'll be a combination of a radiologist and an AI, and that will be more efficient than a radiologist alone. But the good news about healthcare is it's very elastic. If we can make doctors more efficient, we can all get a lot more healthcare.
Yeah.
So there won't be unemployment, there'll just be a lot more healthcare, which will be great.
It's a good thing. And in healthcare as well, apart from radiology, do you see other places like diagnosis, really complex diseases perhaps that can be made more treatable by AI?
There's two things there. Diagnosis will get much better. We already know from more than a year ago that if you take difficult cases to diagnose, then AI gets about 50% right, and the doctors only get about 40% right. The combination gets about 60% right, and that'll save a lot of lives. In North America, about 200,000 people a year die of bad diagnoses, so it'll have a big effect there. And that's from AI from more than a year ago, so it'll get much better at that. It'll also, of course, be better at designing drugs, so we'll get much better treatments.
We're already seeing some of the early-stage drugs designed by AI going through clinical trials, so it is an exciting time for that, and speeding up clinical trials as well. So that's one area. There you go, medicine and healthcare. As if that wasn't enough, is there another one you want to talk about?
Yes, the next area is education. So my university doesn't like me talking about this, but AI will be much better at tutoring people. So we already know that if you take a child and give them a personal tutor, they learn about twice as fast as in a classroom. And that's because the personal tutor understands what it is the child doesn't understand and tailors their explanations to what the child's understanding. AI should be able to do that even better because AIs will have had experience with millions of children to train on. This will come in the next 10 years or so. It's not there yet, but it's coming. And so we'll get much better education at many levels. I think the last level where that'll happen is educating PhD students, because that's more an apprenticeship. It's not so much teaching facts as teaching approaches, but it'll come there in the end too. We're already seeing it in companies for educating employees. So I work with a company called Valence that has a system called Nadia that teaches employees leadership skills. And we're going to see in all companies, I think, AI being used to educate employees. When I was at Google, I used to have to do training videos, which were very boring, on how to be polite and things.
Did they work?
To some extent, yes. I think interacting with an AI tutor would actually be much more efficient and less boring.
People can attest to that in this room probably as well, having just personally tried out chatbots and things to ask questions. And obviously you have to be careful what you believe, but it's a good start, right, already, and you can see where it's going. Okay, give us one more hopeful case, the one that you think is going to be one of the most optimistic and visionary things that AI will be doing in the next 10 years.
So I agree with Demis Hassabis, the leader of DeepMind, who for many years has said AI is going to be very important for making scientific progress. It's going to make scientific discoveries. There's one area in which that's particularly easy, which is mathematics, because mathematics is a closed system. So you're going to get AIs that play mathematics. That is, they ask themselves, I wonder if I could prove this, I wonder if I could prove that. And because it's a closed system, they can just try things out and see if they can prove them.
So we're talking the mathematical conjectures that are still yet to be proven by humans.
Yes.
Can be amenable to this.
And new conjectures they'll make too. And I think AI will get much better at mathematics than people, maybe in the next 10 years or so. And within mathematics, it's much like things like Go or chess that are closed systems with rules where they can generate their own training data. So when they first taught Go to AIs, they would mimic the moves of human experts. And there's, of course, a limitation to that, which is you run out of human expert moves, and humans are only so good. But then they got what they called Monte Carlo rollout, where you say, if I go here, he goes there, I go here, he goes there, oh, whoops, that's bad for me. And you can learn from the Monte Carlo rollout, and you no longer need humans to tell you what good moves are. You can figure it out. It'll be the same in mathematics, and we'll get mathematical systems much better than people, I believe. And
they don't need breaks or food to eat. They can just carry on continuously and get to solutions much faster than humans might before they get tired, right?
Eventually, yes.
Yeah. I mean, in general, then, mathematics is something you think will be amenable to this. But is science in general, research in general, so physics, chemistry, molecular biology, will all of these things, you think, be accelerated by the neural networks of the future?
Yes, I think what we'll see is little bits of those scientific enterprises will be accelerated early on, and as time goes by, more and more aspects will be accelerated, yes.
And what will that world feel like to be in when AI is accelerating scientific progress? It feels like scientific progress is moving fast right now. If it gets even more exponential, what does that mean?
It could make life much better for everybody. If we share out the benefits of the increase in productivity, it'll be great for everybody. So one example now already, if you get a full-body MRI scan every year and you get AI to interpret it, basically you don't need to die of cancer anymore. You can detect almost all cancers when they're very small. And if you can detect them at stage one, you can normally just get rid of them. So Craig Venter, who was one of the people who sequenced the human genome, had full-body MRI and detected 2 very aggressive prostate cancers, much like Biden may have now, very early, and was fine. So with AI doing the interpretation and doing better interpretation than people can do, we'll get things like that that'll basically get rid of people dying of cancer if you can afford the full-body MRI.
I was going to say there's a could in your statement, and we'll come back to the equity and the sort of general how this stuff is going to roll out a bit later. Let's talk a bit about the AIs themselves now, so not just the applications. Are there things that you see models being able to do in, let's say, 5 years' time that they can't do now?
I'm very cautious about making those predictions because of my false prediction in 2016 that we'd by now have AI radiologists replacing ordinary radiologists for reading scans. It's very hard to see 5 years ahead. The best way to understand how hard that is to look 5 years back. If you look 5 years back from now, we were just beginning to see things like GPT-2, which seemed amazing at the time because it could generate coherent text. We never had things like that before. The coherent text wasn't very good and was full of nonsense, but it was coherent. If we look at that now, it seems incredibly primitive. So I think the best I can say is the things we have now will seem incredibly primitive in 5 years' time.
So we'll be surprised.
We'll be surprised. For example, they'll be able to do much better reasoning, and I think we'll get far fewer hallucinations. I think things will be, the AI chatbots will be able to do reasoning about what they just said and realize that doesn't really make sense, and they don't really have good evidence for that. And so they'll be far more like people in that respect, people who want to tell the truth, and they will be much better at not hallucinating.
Let's talk about reasoning, which is something that the latest generation of frontier models have been doing for the best part of 6 months or so, at least in the public anyway. Was the timescale that arrived with chain of thought, all of those things, was that did you expect that to happen at this sort of rate, or was it a surprise?
It was a surprise. So if you'd asked me 10 years ago, I would have confidently predicted we wouldn't have chatbots you could talk to about anything. We wouldn't have a system like GPT-4 or Gemini 2.5 where it's a not very good expert at everything. That would have seemed extraordinary. I'd have said that was way further off. And we certainly wouldn't have systems that could do complicated reasoning. And now we have, the reasoning's getting up to human levels. So I've been very impressed with chain of thought reasoning and with using reinforcement learning to learn the chain of thought reasoning rather than having to have people demonstrate the chain of thought reasoning. And this has completely changed our model of what reasoning is about. So for many, many years, AI was dominated by symbolic AI, which thought that reasoning was the essence of intelligence, but was completely convinced that the way to do reasoning is like logic. You have to take English sentences and convert them into some kind of logical form to which you can apply symbolic rules to derive new logical forms, and that's what reasoning was going to be like. And they were so convinced about that, they didn't really think it was a hypothesis. They thought that's just how it has to be. That's just fact, yes. And those people now have withdrawn to saying, well, we're going to have hybrid systems. We're not going to be able to do reasoning until we have a hybrid system where you use AI to convert reality into the kind of thing that these logical systems can deal with. You take messy reality, convert it to that, and then these logical systems do the reasoning. So there's still a movement that says we need hybrid neural net symbolic AI. I think this is complete nonsense. I think chain of thought reasoning has shown that the reasoning is all done in English by systems that know how to understand English. And understanding English does not consist of converting English sentences into logical forms. I can try and give you a model of what I think it does consist of. So I'm going to try and give you a model of what's happening when these big chatbots understand English, or whatever your language is.
Does it work for all languages, what you're about to say?
Yes.
Yeah.
And I'm going to assume that they operate on words, although they operate on word fragments, because it's easier to describe if they operate on words. So rather than taking a sentence made of words and converting that into an unambiguous logical form, what they do is take these word symbols and convert the word symbols into big vectors of neural activity, big sets of active features. And of course, you can't always decide what set of active features you use for a word, because it depends on context. If I give you the word may, that could be a month, it could be a woman's name, or it could be a modal like would or should. And so you don't initially know how to convert it into a big set of features, so you sort of hedge your bets. and then use multiple layers of neural net to gradually disambiguate it, to clean it up by interacting with the feature vectors for other words in the context. And once you've turned these words into the right feature vectors, that is understanding. Now, the interactions are quite complicated that create the right feature vectors. So let's take an example where we understand modeling. If I take any distribution of 3D matter, I can model it up to a certain accuracy by using Lego blocks. I can take the shape of a Porsche. If I'm not worried about the shape of the surface, I can model that shape quite nicely with Lego blocks. So Lego blocks can model any 3D distribution of matter up to a certain resolution. Words are like Lego blocks, but for modeling anything. So Lego blocks are three-dimensional. Words have feature vectors that are maybe 1,000-dimensional. So they're much more complicated. What's more, each Lego block, each word, has a name, which is the name of the word, but that doesn't totally determine the shape. In Lego, you have different shapes of Lego blocks, but they're not deformable. With words, they're deformable, and they deform to fit in with the other words in the context. So that gives you shades of meaning. Also, the way they interact is more complicated than Lego blocks. So Lego blocks, you have a little plastic cylinder that goes into a little plastic hole, and that's it. With words, if you want a model of what's going on in chatbots, think of each word as like a high-dimensional Lego block that's got an approximate shape, but that will deform to fit in with the other words. And think of the Lego block as covered with little hands. And as you deform the Lego block, the shapes of these hands changes. And they have to shake hands with other Lego blocks. And they have to choose which other Lego blocks to shake hands with. That's called attention. Multi-head attention is these multiple hands. And so for a normal person, a good model of what's going on is the names of the words tell you which Lego blocks to use. The Lego blocks are deformable, and they deform around to try and shake hands with other Lego blocks in the context to make a nice structure. Once they've done that, that's understanding. And you can see it's quite like the protein folding problem. With proteins, you have a bunch of amino acids, and you have to figure out what shape they're all going to make. Which amino acids shake hands with each other amino acids. So understanding is much more like protein folding than it is like turning each sentence into a logical form. So the whole model that linguists and symbolic AI people have had of understanding is just wrong.
You think it's neural networks all the way?
It's neural networks all the way. And the people who say we need hybrid neurosymbolic systems are the old-fashioned people who used to believe in symbolic systems, who want to retain some of that. And they're a bit like people who make petrol engines. If you take people who make petrol engines, that actually electric motors are better, they might come back and say, we agree, electric motors are great. What we're going to do is we're going to use electric motors to inject the petrol into the engine. That's what neurosymbolic AI is like.
OK, well, interesting. I think that I get a sense from you of where you think it's going and where the sort of signal is versus the noise. A lot of people still talk about symbolic AI as necessary to augment the neural network architecture. But I think, as you said, and that's been demonstrated, neural nets seem to be able to do a lot more than even perhaps you thought initially.
Yes.
So I think that if they're surprising you, they're probably surprising quite a lot of people. I want to talk about the sort of other sort of challenges for making models behave in the real world in a more sort of natural way. So things like bodies. The human mind is not only in the brain, there's intelligence all around our bodies, getting feedback from the world, responding to those things, the spatial awareness, all these things. All obviously controlled by the brain, but sort of also it's distributed around us. I'm curious to hear what you think about that in terms of the models we're working with. The models are all in silicon right now. They're all in the virtual things in computers. But at some point, do you think that to make them more realistic, to make them more useful, they're going to need bodies, sensors, spatial awareness? And if they do, how are they going to get that? Is that going to be programmed in? Is that going to be learned? What's your thinking on this?
OK, so there's a distinction to be made here. There's a philosophical question and a practical question. So philosophically, you could ask, if a child just listened to the radio, could they learn about the world? The only thing they do is listen to the radio. And philosophers will often tell you they couldn't. But actually, what's happened in chatbots is they've just seen strings of text, and they have learned about the world. So there's a remarkable amount about the structure of the world that is implicit in the sequences of words.
A lot of meaning in language.
Yeah. Yes. But that's not the most efficient way to learn about the world. These chatbots have to see immense amounts of text to learn about the world that way. It's much more efficient to learn about the world if you can interact with it. So having a camera and having a robot arm will enable you to learn spatial stuff much more efficiently. But that doesn't mean that's the only way to learn it. You might be able to learn a lot about space just from language, but you can learn it much more efficiently if you're in the world and can do experiments on the world. You don't have to be able to do experiments to learn about the world. Some people think you do, but if that were true, astrophysicists would be kind of out of luck.
Yeah, I mean, so in a sense, all the robots previously robots have been trained by programming rules into them, essentially. If you detect this, do that. And it's been very meticulous and slow, whereas I think the equivalent of large language models in movement have shown that you can just move the robot in different directions or allow it to make mistakes. And as long as it's not doing anything dangerous, it will learn how to do things.
Exactly.
So the architecture works, even in movement, as opposed to language
yes,
as well.
A lot of progress is being made in robotics. They're making things that have a sense of touch. I think Amazon recently had something. It took over a company called Covariant, and I suspect this comes from Covariant, that they have very good AI for physical manipulation, and you combine a sense of touch, and you get very good things for picking out the right Amazon product to put in the box.
I mean, the idea of the dark warehouse where there's no people working, it's just robots, it's not even science fiction anymore. There are those things. I suppose they're still dangerous for humans to operate in because robots aren't good enough, but at some point, the human-robot interaction will be able to happen if the robots are better. Yeah.
Yes.
Can I ask you about some bits of hype and buzzwords that people talk about these days? So 2025 was always going to be the age, or the year rather, of agentic AI. AIs that can be agents that can do things in the world. And many companies selling products, we're told that you can set your LLM off to book your holidays, not quite yet, but soon. What's your opinion of this? Is this actually something real, or is it a little bit of hype?
I think it's real. I think we're seeing it. I think we're even seeing agents interact with other agents, which is slightly scary.
What useful things are they doing then?
Let's see. If I was still doing research, I would probably know all the details of this. I just read about it. Agents can do things like make bookings on the web. I assume agents will pretty soon have your credit card number and be able to just buy things for you. Agents can interact with other agents to do quite sophisticated planning. So we are getting agents. It's not just hype. And in general, I've lived through many years of people talking about AI hype. And in the 80s, when we started using backpropagation, we were very enthusiastic, and we got sort of slightly ahead ourselves. And we thought fairly soon we'd be able to do lots of things we couldn't do for a while. So there was hype then. But my overall opinion is in the last few years, if anything, AI has been underhyped.
Because of the rate it's going at? So this is my next question. The people talk about the scaling laws, more computing, more innovation, more money going into these things, more clusters of computers being built, more chips. So if you just keep doing more, you'll get even faster, get further even faster. Do you think there's a limit to this at any point?
There is a limit unless you can generate your own training data. So with language models, most of the data in the world is siloed in companies. The freely available data has largely been used up. And so they are beginning to hit a limit. They're also hitting a limit where the amount of progress you make by scaling up is logarithmic. To get one extra little bit of performance, you need to double the amount of data and double the amount of computation. The next bit, you double again. So that's hitting a limit, and it's hitting an energy limit now. But for things that can generate their own data, you're not going to get a data limit. And I think even things like language models will be able to generate their own data by using reasoning. They'll be able to say, I believe this and I believe that. I can do some reasoning and say, so I ought to believe that, but I don't believe this other thing. So now something needs to be fixed. I need to fix one of the premises, or I need to fix the conclusion, or I need to fix the way I do the reasoning, but I can get a gradient to change things. And that's how things like AlphaGo learn to be much better than people, and it's how language models may learn to be much smarter than people.
I'm curious to know if you think there are sort of foundational architectures that will change or need to be developed to sort of push beyond that one difficulty that you still talk about, which is that to get better, you have to double the amount of data. You have to keep doing that. Of course, we can keep doing that. But are there other architectural things in the next few years or the next decade that you hope either will come, or problems that you think might be solved by changes in architecture that you think need to happen to really push this forward?
So I think there's two things here. We know that there's still lots and lots of progress that can be made by doing better engineering. And DeepSeek was a wonderful example of that. DeepSeek did better engineering to make use of old NVIDIA chips, and they did better engineering in the training. They did sort of piggyback on big chatbots trained with much more compute power. So there's engineering improvements will continue to happen, and so will allow us to do the same thing for less energy. But inevitably, there will be scientific breakthroughs. They're almost impossible to predict. We don't know when they'll happen. But I don't believe that things like transformers, which Google produced in 2017, made a big difference. I don't believe that's the last big breakthrough we'll get. We'll get other big breakthroughs in the architectures, as well as big breakthroughs in how we use those architectures. Like the recent idea that you should do much more computation at test time. So the computation isn't all in the training, and then at test time you do some fixed thing. You actually can do research at test time. That's making a big difference. But there will certainly be more breakthroughs in the architectures that we haven't thought of yet.
Tell me about short-term memories that LLMs might have. We've talked about this before, actually. I'm curious to know why you think models need a short-term memory and what they can do with that.
OK, so for quite a long time in neural nets, people's view of how you would deal with sequences were that you would have a recurrent neural net, and the recurrent neural net, all its information about the past of the sequence would be stored in the activation states of the hidden neurons. And these activation states change with each word. And so those are the things that are changing rapidly. And then there'd be things that change slowly, which are the connection strengths that determine how the input word and the current activation strengths lead to the activation strengths of the next time step. That's a recurrent neural net. And for many years, people thought that's the way it's going to go. Then transformers came along and said, no, look, we're going to keep all the previous activity states, and we're going to allow the current word to look at all those previous activity states. So we're keeping around a hugely more context. And that worked much better. Now, if you ask, well, how could the brain possibly do that? The brain can't possibly keep around all the previous activations of the neurons. It's only got the same neurons. So how does it get that kind of hugely rich context? And it's clear the only way it can do that is by having memory in short-term connection strengths. So the classic neural net model says you have neural activities that change fast as the data comes in. You have connection strengths that change very slowly and learn over many, many sequences. And that's it. There's just two timescales. But you can't do transformers in a real neural net like that. You have to have a third timescale at least, which is that you're going to take your connection strengths and you have an overlay on those connection strengths that we call fast weights, which rapidly changes the connection strengths in a way that decays rapidly and can contain much more information than the neural activities. Thousands of times more information than neural activities. And that's the real context these neural nets are operating in. That's what must be going on in the human brain to do anything at all like what transformers are doing. It gives you a hugely richer context. So that's a nice case where progress in AI that looks very unneural has actually led to progress in the way people think about how the brain is handling sequences. It must be having temporary changes in connection strengths to act as a big context.
So fast weights, you heard it here first.
Yes.
That's the thing to look out for in the next few years. And just one more bit on the science before we talk about the sort of safety aspects of all this, which is you started your career trying to understand the human brain. And you've ended up in this place where you've created essentially a version of that in silicon Do you still get fascinated by the brain itself, the human brain? And what do LLMs and the latest generation of like neural networks tell you about our own brains?
So actually, yes, I had a career that's designed to understand how the brain computes, and I failed. But in that failure, we produced other stuff. In our attempts to model the brain, we produced things that learn using backpropagation. I now believe that the brain probably doesn't use backpropagation. The brain is solving a somewhat different problem from these large chatbots. In the large chatbots, you have trillions of training examples, and you only have of the order of 1 trillion connections. Your brain is very different. Your brain has 100 trillion connections, but you only live for a couple of billion seconds, slightly more, which is lucky for me, but only a couple of billion seconds, and so you don't get much training data. So the brain is solving the problem of, with very limited training data, how do we learn using huge numbers of connections? The AIs are still solving the problem of, with a huge amount of training data, how do we learn using not many connections, where not many is now 1 trillion? The backpropagation learning algorithm, which all these systems use, is great for solving that problem. How do you squeeze lots of information into